In this video, we consider the language L, which is the set of strings description of M1, M2, such that M1 and M2 are Turing machines, and the string ABA is an element of the language M1 union language M2. So what we're really saying here is that the string ABA is in either the language of M1 or the language of M2 or possibly both. We want to show that L is recognizable but not decidable. Okay, so let's start on L recognizable. Okay, so in thinking about this problem, we know that ATM is recognizable. And this problem is similar to asking, does M accept W? Except we're going to ask it for M1 and M2 instead of just M. Okay, so some things that we know, some facts to think about. ATM recognizable. And what was ATM again? ATM was the set of strings MW such that M accepts W and M is a Turing machine. Okay, so you can see here if we're asking does M1 accept ABA, does M2 accept ABA, that it's similar to running two instances, let's say, of ATM. Okay? You might be tempted to construct a recognizer that first runs M1 on ABA and finds out what its answer is, and then runs M2 on ABA, finds out what its answer is, and then accepts if either one accepts. Okay, so let's try our first proof. So let's say that R is a recognizer for L, and what would it do on input M1, M2? What would we try to do? Simulate M1 on ABA. Okay, so I claim that this is not actually a recognizer for L. Notice here that we only go into step 2 if M1 halts and rejects on ABA. Okay, so what happens if M1 does not accept ABA, M1 runs forever on ABA, but M2 will accept ABA? What happens is that we never actually get to step 2. So, because M1 runs forever on ABA. So, even though this string M1, M2 should be recognized in the language L, it won't be. This will run forever. Okay, so we can't do this. Alright, so instead, what we're going to try to do is run or simulate M1 and M2 in parallel. Basically, we have to make sure that one or the other machine can't run forever, preventing us from finding out that the other machine accepted the string. Okay, so we're going to do this in parallel. Okay, what does that look like? Let's make a new recognizer. Let's call it R prime. And on input M1, M2, what are we going to do? Here we have a loop. Okay, for I equals 0, 1, 2. Okay, so I is going to take on these values. Technically not 0. Let's just take that one out. It would still work, but it's not needed. I don't mean run. I actually mean simulate. Okay, so why does this work? Well, first of all, what does it actually do? It says when I start up my recognizer, I'm going to let I equal 1. So I'm going to simulate M1 on ABA for 1 step. This means I'm going to take, say, 1 transition on M1. And if I reach an accepting state, then I'm going to accept. Otherwise, I go to B. Now I'm going to simulate M2 on ABA for 1 step and accept if it does. If neither one of these accepts, we go back up to the top of our loop, and now I is 2. We're going to simulate M1 on ABA for 2 steps and accept. Then we simulate M2 on ABA for 2 steps and accept if it does. So what this does is it prevents one machine from running forever when the other machine would accept ABA in a finite number of steps. So remember that for a Turing machine, if a string is in its language, it recognizes that string, it has to do so in a finite amount of time. It may run forever or reject on a string that's not in the language, but if the string is in the language, it has to halt and accept in a finite number of steps. Okay, so if ABA is in either M1 or M2, then when we reach the value I, for which that machine would accept ABA, it's going to do so. Okay, and so here we can find out in a finite number of time if either one of these machines is going to accept ABA, and then we accept. Okay, so this is a recognizer. Notice that it's not a decider because if the string is not in the language, so ABA, or in this case M1, M2, so let me write this. We'll make it precise. If M1, M2 is an element of the language L, then either M1 or M2 or both will halt and accept ABA in a finite number of steps. Okay, and then when that happens, then R prime halts and accepts M1, M2. Okay, so this is exactly what we wanted. However, if M1, M2 is not in L, then or M2 or both may run forever on ABA, right? Then R prime runs forever on M1, M2. Okay, notice here that R prime may halt and reject. M1 and M2 may both halt and reject ABA, but it's the case that either one or the other may run forever on ABA, and when that happens, R prime naturally runs forever. Okay, so this makes R prime a recognizer, but not a decider. Okay, so notice here we haven't proved that L is undecidable. We have simply proved that L is recognizable. Because we've constructed a recognizer to recognize L. Okay, in order to prove that L is undecidable, we actually have to do a proof by contradiction. Okay, so remember that we've talked about how to do this proof by contradiction. Basically, if we want to show that, so if, I'm just going to call it A at this point, A reduces to L and A is undecidable, then L is undecidable. Okay, so all we need to do is find A that we can show is undecidable, or that we know is undecidable, and we can show it reduces to L. Okay, so this is going to be our proof by contradiction. We're going to suppose L is decidable. We're going to let D be the decider for L. And then we show that ATM reduces to L. Remember that we know that ATM is undecidable. So if we can show that ATM reduces to L, then this decider D, that's the decider for L, cannot possibly exist. Okay, and here's how we're going to do it. Oh, I'm going to call A the decider that we're building for ATM. Okay. On input MW. We're going to use the description of M that we received as input, as well as the string W. To construct a new Turing machine that we're going to call, let's call it M prime. Okay, here's the description of M prime. On input W, if W is not equal to ABA, reject. Else, otherwise, M prime is going to simulate M on W and accept if it does. Okay, so it's just going to run the transitions by reading, basically, when we construct M prime, we're going to include the description of M in M prime. Okay, so you can read step 2 as saying that M prime is going to basically do the same transitions that M would do on W. Okay, and therefore it would end up in an accepting state if M ended up in an accepting state on W. Okay, so that's the description of M prime. And here we're back to our description of A. So this is the outer. Okay, so otherwise, let's see, part of A says we're going to build this new Turing machine M prime, and then we're going to run D, which was the decider for L, on M prime, and accept if it does. Otherwise, we're going to reject. Notice that we did not build M prime to actually run it. At no point in this proof are we saying actually run M prime. We just constructed it in order to feed its description to the decider D. Okay, so it doesn't matter that M prime may run forever on W. Okay, so convince yourself that that's the case, because we're never actually going to run M prime. We're going to use the decider D, which we know must halt and reject, must on all inputs. It's either going to halt and accept or halt and reject, and that's why it's a decider. We're going to run it on the string M prime, M prime. Okay, so we're just going to give it M prime and M prime. And then we're going to be able to accept if it does and otherwise reject. Because it's a decider, it's going to do one or the other. So we can do one or the other. Okay, so let's prove to ourselves that this actually constructs a decider for ATM. Okay, that A is actually a decider for ATM. So if A rejects, it does so because D rejects M prime, M prime. Okay, when does D reject M prime, M prime? It's going to do so when W is not ABA. Okay, or also if M does not accept W. Okay, but if W is not ABA, it's definitely going to reject. So, okay, note here that this actually won't work in the case that, so the one caveat here is that if, I don't know if I should go into this detail, if we're checking to see if M, the original machine M, accepts ABA, if M does accept ABA, it's going to give us the wrong answer. But that's only one string. So we have one string exception out of the entire universe of all possible strings. So we're going to keep going with it. But for any other string, W, if D rejects M prime, it's because M does not accept W. Okay? Therefore, this gives us the case that M does not accept W. What happens if, oh, let's see if I can get down here. If A accepts, it's because D accepts M prime. Okay, when does D accept M prime? It does so when ABA is in the language M prime or M prime, which is, or is in the language recognized by M prime. So let me take a step back real quick. Let's look at the description of M prime. As long as W is not ABA, M prime is going to simulate M on W and accept if it does. So this means that D is going to accept M prime if M accepts W. Okay? So here we have a decider for ATM. The decider is A. It's going to use this supposed decider D for L. Therefore, because we know that ATM cannot be decidable, A cannot exist, and therefore we have a contradiction, and D cannot exist.